Okay, perfect. So let's start. Welcome everybody to a new IPARCOS seminar. Today it is a pleasure to introduce Alfred Castro-Ginard from the University of Leiden. Alfred did his physics degree in the Balearic Island in Mallorca, and after completing the physics degree, he started his PhD in Barcelona under the supervision of Carme Jordi and Xavier Luri. Using basically inside this world of the Gaia mission and working with Gaia data. And after completing the PhD this year in 2021, he moved to the Leiden University to work in collaboration with Professor Anthony Brown, in where he's now doing a lot of very interesting research on, again, analyzing now the real Gaia data. So today we will have a very interesting talk about that, about the open clusters discovered using this amazing new Gaia data. So if I missed something, I know that you are also in many other projects, involved in many other projects. If you want to add something else to this introduction, please feel free. And if not, you can start when you want with the presentation. Thank you a lot for accepting the invitation.
Thank you for inviting me. I will not add anything. So now you should be able to see my screen. Yeah.
Yes, we can see it. Yeah, perfect. Okay.
So, well, yes, what I'm going to explain here is the work I did basically during my PhD, which is the search for open clusters in Gaia data, and now apply it to EDR3 and to see the deliveries for EDR3. I included here the logos from the Sterrewacht in Leiden. That's who I am now, but basically this work was developed at the University of Barcelona. Okay, so first, a bit of introduction. I'm not going to take a lot of time here because it is mostly known to everyone. So what are open clusters? Basically, they are gravitationally bound stellar groupings that were born on the same molecular cloud. So they share ages, they share initial chemical compositions. They also share location, velocities, and so on. In terms of Gaia observables, that's what we are interested in. It's the first time we can describe these objects using high dimensionality space. So in this case, we will be using 9 dimensions to describe them homogeneously. So this will be 6 dimensions for astrometry. So these are finding stellar over densities in L and B, which are the sky angles, parallax, the proxy for distance, proper motions, and radial velocities. For the time being, we will only use the first 5 dimensions because we don't have radial velocities for all of the stars, but ideally we will use them as well. And then we can also describe these objects using 3 additional dimensions, which are Gaia photometry, basically. So we know that these objects will follow an isochrone pattern because they are born, I mean, they share the same age and chemistry in a column magnitude diagram. And for that, we will use the Gaia photometric bands where G, BP, and RP. So very, very quick introduction about Gaia, since we will be using its data. It's a scientific mission, and satellite was launched in 2013. The data deliveries are scheduled in different stages. We had the first delivery in 2016, counting with 1 billion sources, but only with positions and magnitudes. And within this release, we had the TIGAS data release that was around 2 million sources with also parallaxes and proper motion. Then a big step forward came with DR2. For me, it's like the biggest step forward here, where we have already around 1 billion sources with all the parameters, right? So positions, proper motions, parallax, and also photometry in the 3 bands. So we can exploit this methodology I will present. The latest release is EDR3. This is a similar number of objects than the DR2 one, but with much improved positions. These are around 30% in parallax, and the biggest improve is around a factor of 2 in proper motions. And then will be third release complete. So it will be completing the early third release by next year, and then the final release, don't know when. So let's jump into the method. Why are we motivated to develop this method? So we're motivated to find new structures in Gaia. As I said, it's the first time we can describe a lot of stars with this high-dimensional space. First, we devised the methodology and we tested using TIGAS, which is a smaller sample and controlled sample. We adapt this methodology to work with Gaia DR2 in different density regions. And then we perform big data search, I call it, in the whole galactic disk, where we analyzed hundreds of millions of stars together. And now the last work, which is under the referee now, is expanding the open cluster census using EDR3. And to do that, we did that because we wanted to test basically the cluster completeness, cluster population completeness, because we thought that the census was complete in nearby distances. We could test that using TIGAS already. And we saw that when trying to catalog open clusters, so when trying to characterize open clusters catalog previous to Gaia data, we could only validate like around half of them. And we already found a lot of new objects by chance, let's say. So we wanted to automatize this search. Okay, so the method, now we call it OC Finder, like Open Cluster Finder. It's not a very new name, but okay. So it's a data mining methodology to automatically search for these clusters in Gaia Archive. I said here Gaia DR2, but it's in any release. The method is based on two machine learning algorithms. First, as I said, the detection of overdensities in astrometric space. For that, we use unsupervised learning, so we don't know what we are going to find. We try to detect stars that share common properties, and we use that, and we do that using the Hdb Scan algorithm. We'll explain more about this after. And then we use a supervised learning, so we classify these overdensities into mere statistical overdensities or real open clusters by looking at their CMDs, so column magnitude diagrams. And we do that using an artificial neural network. So this is an overview of the methodology. Basically, we start from Gaia data. We do kind of pre-processing step. This is quite usual in machine learning pipelines. I will explain more about each of the processes. Then we run Hdb Scan, which is finding overdensities. You cannot see my cursor here, but I hope you can follow my words. So we run Hdb Scan. I said here there is a shift because we run Hdb Scan into small regions to account for local overdensities, let's say, and then we shift these regions to account for clusters in the borders. And this results in a list of Hdb Scan clusters that can say real cluster or just statistical clusters. And we distinguish between both using an artificial neural network that is trained on color magnitude diagrams of non-clusters, so well-studied clusters. And then this results in a list of new clusters. Okay. So first step is the pre-processing. First, we reject stars with hyperpromotions that will not be compatible with disk rotation, where clusters are expected to follow, or high parallaxes to account basically for projection effects. We will not see as an overdensity a cluster that is very close by because of projection. We divide the whole disk, this is our region of interest, into smaller regions, and I already explained the reason. This is because we want to find overdensities, and in order to find meaningful overdensities, we need to define a meaningful average density of the region. So that's why we divide into smaller regions. We consider only the galactic disk. This is because we expect to find clusters there. And and as I said, we shift the regions to account for clusters in the borders. Then in each of these regions, we run the Hdb Scan methodology. This is a density-based and supervised algorithm. We chose Hdb Scan because it requires no a priori knowledge of the number of clusters. So we don't know how many clusters we're going to find. So we need this feature in our methodology. It confines arbitrarily shaped clusters. that can account for projection effects as well. So we may not see a nice Gaussian shape if we account for projection effects. And the thing is that we need to define two parameters. So one would be epsilon, and the second one would be the minimum number of points for us to consider a cluster. And this is represented here in this is represented here in this sketch in 2 dimensions. So basically here we have all the points, let's say dots, squares or triangles that will be representing stars. Then what Hdb Scan does is for each point, it builds an epsilon neighborhood. In this case would be a circle in 2 dimensions with radius epsilon. In the general case, it will be like an hypersphere in n dimensions. In our case, will be 5. So it builds this epsilon neighborhood, and it looks for stars within the epsilon neighborhood. Right? So in the red square, basically it cannot find any star within his neighborhood. So it will be a field star. Then we go to the green cases where we can find these three other stars. I mean, in total, there are 3 stars within the epsilon neighborhoods that will be core members of the cluster. In this case, we require the minimum number of stars being 3. And then there is the blue case, which is not a core member, but is a member of a cluster because it's reached by an epsilon neighborhood of 1 core member. We do not distinguish between these two, but the algorithm can. So to account for distances between stars, we use this statistical distance, which in our case is the Euclidean one, with the standardized parameters to account for different ranges of every parameter. So from now on, when I talk about distance within stars, I will be talking about this statistical distance. This is a visualization of how Hdb Scan works. So basically, it does what I already explained. So it goes point by point, build this epsilon neighborhood, and find for n number of stars within the neighborhood. If the requirement is satisfied, then it considers the clusters. If otherwise, there's these black empty circles that are appearing every now and then. So there is just a visualization for you to see better how it works. Okay, so how do we compute this? The parameters for the Hdb Scan. First, this is the epsilon parameter. Well, let me explain the other two, which are the easiest one. So the minimum number of points plus the sizes of the regions that we use to search for the lower densities. They are chosen using simulated data. So basically, we use Galaxy. The Samsung Galaxy model plus simulated clusters, and we run the whole methodology, and we just select the optimal values of this minimum number of points and else. By an optimal, I mean the values that can detect most of the clusters. Okay, so this is one side. And then on the other side, we use the epsilon value. We compute it automatically in each of these L by L in these model regions. And basically, we use the fact that stars within a cluster are closer together than random field stars. And this can be seen in this plot here, where you can see the distribution of distances between stars. In this case, we use the distance between each star to its 7th nearest neighbor. And we see in blue the actual distribution of the stars, where you have this blob towards smaller distances that will belong to the cluster. In green, there is the distribution of the actual cluster there. And we want to isolate this blob from the field distribution. And to do that, we reshuffle the stars. So we remove all the structure. And we plot again the same plot, which will be the orange curve. And we try to compute the epsilon as the value which is in the formula here, which will be the minimum number, the minimum epsilon in the blue distribution, the minimum epsilon in the orange distribution, and just a mean, so we can isolate the blob here. Okay, so we do that using a big data environment. In our case, this is the Mare-Nostrum supercomputer. There are a few features of the Mare-Nostrum supercomputer. It was top 1 in the world, I think, at the end of last year. It's not anymore. It's been superseded by Summit, I think. I don't know. But even if it's not the top 1 in the world, computer is the most beautiful computer in the world. And this is something it was said by these guys. It is because it's in a chapter, right? So I encourage you to visit my nostrum if you ever have a chance or you ever in Barcelona. Okay, so how do we do this? We run only the Hdb Scan in parallel in this supercomputer. This means that we are able to run around 100 millions of stars. In the case for the DR2 search, we ran this methodology integrated disk up to magnitude 17, and this was like 100 million stars. But they are not all analyzed together, right? Because we are dividing these into these small regions, and this is what is in the right hand of the slide. So we run basically Hdb Scan on tens of millions of stars instead of hundreds. This is already a step forward from other methodologies. I've quoted here a few for comparison. Basically, the first one, we were able to analyze around 7,000 stars. This is, in our case, we run it for order of magnitude more than that, and this can remove some biases in the search, right? And basically, what we do is a two-level parameterization. Let's say first will be a distribution, so computing each of the boxes simultaneously, and then if in each box there is a lot of stars, so we parallelize the distribution, the calculation of Hdb Scan. And now in the last work that we did using EDR3, we went to magnitude 18. So that means basically doubling the number of stars in the same order of magnitude. We could go farther because there is not a limitation for in the computational framework, let's say. But the thing is that if you go deeper in magnitude, that you are dominated by errors, and yeah, we don't want that. Okay, so this will be the clustering step. This will be how we compute the stellar overdensities, but then they can be real clusters or just physical or just statistical overdensities, and this will be these two kind of color magnitude diagrams. On the left hand, you have a color magnitude diagram that belongs to a real open cluster, so you see this characteristic isochron shape, and on the right hand you see just a statistical overdensity with its color magnitude diagram. So we want to distinguish between these two cases. How do we do that? So we use a set of well-characterized clusters with well-characterized color magnitude diagrams, and we trained an artificial neural network to distinguish between the two cases. Basically, well, we used a deep learning architecture, which will be very, very similar to this one. I didn't make this plot, I just took it from Google, but it's actually a good example of what we did, because this is to recognize handwritten digits. So we have not handwritten digits, but we have isochrons, so it will be more or less the same case. So basically, there is this first set of blue squares that will be the convolutional layers that basically goes through the image. They go through the image, scanning for meaningful features to then perform the classification, and these features will be chosen in a one-by-one basis. So yeah, in each CMD, and then it flattens all the layers into these green neurons to perform the actual classification. In our case, we will not have like these 10 output neurons, red ones. We will only have 2. That will be cluster or not cluster. Yeah, so to describe this, we better describe the training set. The training set consists on real clusters with Gaia, characterized with Gaia. These are around 1,000, or these were around 1,000 by the time. And we supplement that with simulated isochrons with a wide range of the parameters to cover all the space. Okay, so how complete is our methodology? This is the methodology run on the known clusters by the time of the DR2 release. So In green, you will find the clusters that we are able to find. In red, you will find the clusters that we are not able to find. And in yellow, there are the clusters that we are able to find in the clustering process, but they are not validated using photometry. So that means that they are clustered in these 5 dimensions in astrometry, but then the color-magnitude diagram or the isochrone is, well, not well behaved, let's say, or is too red, or is too distant, or yeah, there's a differential reddening or whatever. So basically, what you can see is that we are limited. Well, the size of the dots are proportional to the contrast between the density of the cluster and density of the field. So higher dots are higher contrast with the field. So basically, what you can see is that we are limited to the highest, to the densest, let's say, clusters in the small regions. And this we know that because in our methodology using the Hdb Scan, since you can only define one epsilon, let's say, so this is this will mean one density threshold. So our way to compute epsilon in the field is towards smaller epsilon, so towards higher contrast, and this we cannot change that. And it is seen in whenever you see a red dot here, it is very close to a bigger green or yellow dot. So that means that the cluster with lower contrast with the field, it didn't get selected. But yeah, we can assess that. And then for EDR3, which is basically the same that for the other 2, we can say that we are, based on the known clusters in previous catalog, we are saying that we are around 80% complete. Okay, so a bit of summary of results. Basically, there is the run in DR2, which is the first paragraph here. We were able to find about 650 new clusters. These are divided into these 3 different studies that are one in TIGAS, not for the nature of the TIGAS data set. These are closed clusters. Right? Then the second paper that was DR2 focused on the galactic anticenter. And then the third paper that was on the whole galactic disk. Okay, so and then this is something surprising and new. The paper is still under the referee process, but we are able to find around 650 more new clusters in EDR3, and there is something that I was surprised about this because I didn't expect this many number of clusters. But okay, this is what it is. We already divide it into categories or class A, B, C, depending on the reliability on the cluster. This is assessed visually by looking at the different distributions in the different dimensions and the color-magnitude diagram and the number of members and so on. And something, if you want to use this catalog, something you must take into account is the numeration of the cluster. So from 1 to around 600 they belong to DR2, and we started the numeration in 1000 for EDR3, just for us to keep the distinction clear. So this is something might be useful. Okay, what are these clusters distributed? This is the new run in EDR3. We see that thanks to the improvements on astrometry precision, we can go to further distances. Well, thanks to the improvements of astrometry precision, we can go to deeper magnitudes, and this will naturally push the search to further distances. Right? So this in the left plot, you see an histogram of the parallax, which is a proxy for the distance, and you see that we discovered very, very few clusters within 1 kiloparsec. So with parallaxes greater than 1, that means further in total further clusters. And this is also seen in the right plot, where there is this ring around the sun of approximately 1 kiloparsec that we don't not discover any new cluster. But that is because of this, because what I said, that the search is pushed to further distances, but also because we have now a better knowledge of this solar neighborhood, let's say. Okay, and this the improvements in astrometry are seen here in the left plot again, where I plot total proper motion error as a function of the parallax, and we see that in DR2, which is the orange lines. Well, I mean, sorry, with EDR3, which is the blue lines, the precision of the proper motions are much improved with respect to DR2, right? So the densest part of the distribution, that would be the innermost curve, is lower here. Okay, so now our application of Hdb Scan is just to detect newer densities, but there is a lot of applications of Hdb Scan. Well, Hdb Scan is a version of Hdb Scan that it's not limited to this single density threshold that I talked about. So it's just running a hierarchy of density thresholds, but this is at the cost of exploding the false positives in your search, right? But okay, so this Hdb Scan here on the right plot, we try to perform the strong chemical tagging, that's called. So meaning search for clusters based on the chemistry. We argue that this is not possible. So basically you can see here clusters, real clusters in the rightmost plot, sorry, and the recovered ones in the left plot. So basically you see that for NGC 6705, which is the cluster in the leftmost, sorry, I cannot use the pointer because you cannot see it. So the cluster in the leftmost part of the plot, it's well characterized using the Hdb Scan, but then for the clusters in the, let's say, bulk of the distribution, so they are mixed together. So basically we cannot distinguish between real clusters based only on chemistry here. And also we can use these kind of algorithms to detect new membership list for clusters. This is in the left plot, where we run Hdb Scan to extend the membership of some known clusters. Okay, so the difficult thing here is not to find clusters, because you will always find something with this kind of algorithms. The difficult here is to distinguish which are real or which are just chance. Okay, so next. Okay, so for this whole population of clusters, also with the EDR3 run, we estimated these astrophysical parameters. So we estimated ages, distances, and line of sight extinctions. And we did that by looking on similarities with known clusters. So they are in the literature known clusters with well studied, with well characterized ages and distance, lighters have distinctions, and chemistry as well. So we basically trained a neural network on these well-characterized clusters and look for similarities within the new findings. So basically what we did is, we used the color magnitude diagram plus 3 other meaningful characteristics of the color magnitude diagram that will be plots for distance. This is the case of the mean parallax, or we will proxies for reddening, or proxies for age, and we let the network decide, given a new cluster, which is the most similar one in the training set, and that will give us distance, age, and reddening for these clusters, for these new ones. So we have now all the new clusters plus in fact, the whole population of clusters that now is 2,500 or so, with not only mean astrometric parameters, but also these astrophysical parameters. We can see a distribution here. This is galactocentering radius as a function of altitude, color-coded by the age. We see that it follows the expected distribution with no high altitude clusters in the inner parts of the disk, except for these ones, which are interesting and might be case for follow-up studies. These are old clusters found at high latitudes. This is interesting. We may follow up on that. I said I have no time for this yet. And in the outer disk, we can see already the flare of the disk with young clusters. This was already seen previously with clusters also. Okay, yeah, we also see if we plot the distribution of these clusters as a function of age for different age bins in the heliocentric XY coordinates, we see that they follow different distributions. For instance, in the top left corner plot, which is the younger clusters, we see that they follow over densities. I mean, that they are grouped in over densities that may follow the locations of the spiral arms. And as you go older and older, these over densities are dispersed, and at the end you cannot see, or you will not trace any of those, and not trace spiral arms. So we wanted to take advantage of this, and what we did is try to characterize the spiral arms using the open cluster sample. For that, we want to detect over densities of young clusters, and by young I mean in this case younger than 30 million years, where the clusters will not, I mean, they have not moved far from their birthplaces, and we suppose that they are born in spiral arms. So we say that these over densities will trace the spiral arms. So basically, we plot this distribution of the clusters in this space, so galactic azimuth and the logarithm of galactic radius, where we see these over densities following more or less the straight lines that will correspond to log periodic spiral arms. We detected these over densities using Gaussian mixture model, allowing for certain symmetry of the over densities. No, so not Gaussian, but elongated in these directions, and they represent the log periodic spiral arms. We were able to detect this many number of clusters assigned to the Perseus local Sagittarius or Scuturam. This is not including the last release for EDR3, but only the DR2 clusters. Okay, because as I said, for the EDR3 is still on the refer process, so I still not do it. And then we feed these lines that will characterize the log periodic spiral arms. Okay, so doing this, we were able to characterize the spiral arms in the solar neighborhood, providing these parameters, or pitch angle, the radius, characteristic radius, and also azimuth. This was usually done using high mass star forming regions, and we could add, but there were only 84 of them, and none of them were on the fourth quadrant because they were seen from ground. And we were able to add around a bit more than 250 young open clusters to these tracers and compute the parameters. There's a comparison between the parameters fitted by rate and collaborators that are the dashed dot lines and our estimations. So we can say that basically they are compatible, and they extend the azimuth, the galactocentric azimuth, particularly to the fourth quadrant, where we didn't have the description of the arms. Okay, so now we have this the arms on the solar neighborhood at the present time, and we wanted to describe the evolution of these arms. So we did it because we have age estimates, and we have radial velocity measurements for this for a subset of these clusters. So we could compute the orbits of these clusters and try to relate these orbits to the birthplaces of the cluster. So basically what we did is for each cluster, compute its orbit to the birth position, then say that the birth position is a location of the spiral arm at the time the cluster was born, because the cluster was born in the spiral arm, and then evolve forward the spiral arm to the present day. And this is, I think it could be done. Yeah, this is a GIF. It's basically what I explained. So the cross will be in this case a cluster. The dot line will be the orbit of the cluster. Then we will relate the birth position of the cluster to a known location of the spiral arm at that time, and then integrate forwards. Not integrate forward. So evolve the spiral arm at the past location with an arm rotation. So basically circular rotation to the present day. So using this, we could compute the pattern speed that the spiral arm was supposed to be moving. And we iterate over, we do like this Monte Carlo-like analysis on the using the error of the edges, and so to iterate over the spiral arms, over the pattern speed to find the optimal value. Yeah, and these are the results. So basically, we could do that for the Scutum, Sagittarius, local, and Perseus arm. So in this plot, it will be from left to right. And we see that the pattern speeds are not, for the different arms, are different, not constant. That will be in contraposition of this study, Monteiro and collaborators 2021. And that these pattern speeds are decreasing when the galactocentric radius is increasing, right? And this will this favors like density wave spiral arms, where you have a single pattern speed which is global and constant for the arms, and will favor more transient spiral arms where they are rotating with the disk. And we independently, we wanted to test the results using this, following the study here, where they studied the distribution of the ages of the clusters along the spiral arms. So basically, in the leftmost plot, you will find there is a density wave spiral arm plotted in gray. And you will find how, due to different rotation of the pattern and the velocities of the stars, you will find how these open clusters travel along the spiral arms, right? And we wanted to see that in our sample. This on the left, on the right plot, you see different setups. So the top left will be the density wave spiral arms and the distribution of the clusters color coded here. In the top right, you will see how is the distribution in bar-induced arms. Bottom left, you see the distribution of the ages of the clusters in flocculent spiral galaxy, and in the bottom right, sorry, bottom right, you will see how is the distribution in tidal, in spiral arms induced by tidal measures. And this is the age distribution in each of the cases. So basically, in the two top cases, you will see this age gradient. This is due to the left. What I explained in the leftmost plot, that clusters are traveling through along the arms. While in the two bottom cases, you will not see this age distribution, and this is because the clusters are corrotating with the transient spiral arms in this case. We were able to see that again in our samples. So these are for the Perseus, local, and Sagittarius arm. I did not compute that for the Scutum arm because we have enough clusters there. And we can see that there is no age gradient of the open clusters along these arms, particularly for the local arm, let's say, but also for the other ones. And yeah, we cannot see the age gradient, and this supports our findings of the corrotating spiral arms, more or less, and by disfavoring the density wave in any case. Okay, and now I end with my conclusions. So basically, this is what I already said. I presented a fully automated data mining methodology to search for open clusters. We could increase the census by 650 objects in DR2 and another 650 objects in EDR3. The total census now is about 2,500, let's say. So this represents the major single individual contribution to the catalog. It's something I like. Yeah, so this was possible due to the inclusion of a data mining framework. Let's have a big data framework, let's say, and we were able to analyze these many numbers of, so hundreds of millions of sources, but only, well, let's say only tens of hundreds analyzed at once, and this gives us a huge advantage over other methodologies. And using this cluster sample, we were able to describe the spiral arms in the solar neighborhood and also trace the evolution for the last, say, 80 million years here. And we could disfavor like this density wave like spiral arms and favor like transit behavior of the spiral arms. And I think this was my last slide. Yeah, that was my last slide. So I will be happy to take any questions or comments or feedback or whatever. Thank you very much.
Alfred, thank you a lot for a very interesting talk. I am really willing to see several of these results after you include the new data from the early DR3, especially the part of the spiral arms. You know that I am really interested in this part. I have many questions, but I will let the people in the audience to ask first. And if they are not asking the same as I want to ask, I will proceed later. So people in the audience, I can see Carmen Gallard. Carmen, please, you can start with the questions.
Hi, Alfred. First of all, congratulations for this really, really great work. I just a very small technical question. In slide number 20, when you show the distribution of clusters as a function of radius and z, is there any observational bias or in the distribution, or is this really tracing where the actual population of clusters is?
Well, yeah. So, well, first, this I did this. I did not go into any detail on this. I just did it just to assess the reliability of the estimated parameters, right? But okay. So observational biases. So in our search, we are limited to the galactic disk. Let's say we define it like. B latitude plus minus 20. So this might introduce some bias here, but I mean, we did that because it is not that we put it on first. So we do not put any limitation on this. Then we run the algorithm and then we just select plus minus 20 because we see that objects found outside this are basically not reliable, let's say. And maybe if I can put some slide here, let me check.
Yeah, but I mean, actually this cut in B could introduce this cone shape, right? I mean, if you would have, for example, selected in making a limitation in Z, for example, then you wouldn't have this possible bias, right?
Yeah, but
still limit within a range of distance from the plane.
Yeah. But the cut is not introduced a priori, let's say. So at first, this you can see this here. So this is a much wider B range, so from minus 40 to 40. Mm-hmm. And then we see that, I mean, so black circles will be the clusters found more times in our methodology, so more reliable clusters. And we see that in the central regions of the disk, this is the size of the cluster. So in the central regions of the disk, we find these clusters to be, I mean, coherent sizes, but then this trend increases in when we go farther from the disk, and we see that this is not physical. So let's say maybe the shapes are, but not the trend is physical, right? So then on top of this, we run the artificial neural network, and a lot of these clusters get discarded as well. And then on top of this, we run the neural network to find ages and distances, line of sight distinctions. That will also give us, if the network converges to an estimation, then will also give us that the cluster is more or less reliable. We can also see that some of these objects are not, we cannot compute ages for them. And this will like give another layer of assessment. And at the end, sorry, I'm explaining all of this. At the end, we see that we don't have any, I mean, we had clusters here, but they got discarded in these different assessment layers. So the ones that finally make it into the catalog are these ones, which are interesting because they are also old. That's something we can expect. But it's not that we didn't have any cluster here at the beginning. We had them, but it just in these different validations of the catalog, they got discarded. Yeah.
Okay.
So, I mean, I'm not saying we are not introducing observational bias. We may be introducing observational bias, but it's not that the result is like this from the beginning.
Okay. Okay.
I don't know if sorry.
Yeah, no, I still, it would be very nice to be sure that really at closer, at lower characteristic radius, you don't have clusters. I mean, that this is a real shape of the cluster distribution. And maybe making all these validations instead of as a function of B, making them as a function of Z would somehow avoid this possible bias.
Yeah, sure. Yeah, but the thing is, but I think we tried, but what happens here is that to get C, to get the cat, then you have to know a good estimation of the distance, right? So we could get that a posteriori because we average over the whole population of the cluster. But if we were to do it first with a single field stars, then you will introduce another kind of bias. So yeah.
I see. Yeah, I understand. Thank you.
Perfect. Thank you, Carmen. We have a question now by Maruza Zerhal. Please, Maruza, you can start.
Thank you. Hi. So thank you for a very nice talk. So you're talking about clusters and you find them as overdensities and you check that they're coeval. But I wonder, do you have any estimate of what fraction of them might be unbound associations, for example? Do you do any checks or?
No, we don't check that. No. And I know that there are people working on this. I know that from the workshop we did about clusters 2 months ago. So there were some people talking about this, and they say that we can expect that results to be out by Christmas time. I don't know, but we do not focus. We do not do that. No.
Okay, thank you.
Okay, thank you, Maruza. And now we have also a question by Patricia. Patricia, please, when you want.
Very nice talk. Thank you very much. My question is related with the ages, with several things. Do you have an estimation of the error that you have on the ages of the, more or less?
No, yeah, well, so to estimate, we do not estimate errors on individual estimations of the age, but we do assess them then statistically, let's say. So basically what we do is to compare the new estimated, because we have this set of reference clusters, right? That and then we train the network with this set of reference clusters, but we also estimate parameters for this. So we can compare them afterwards. And we assess the errors based on the ages, maybe, and the number of members. So basically, in the paper here, which is Cantat Guadan 2020, you will find some plots assessing the errors estimates. I did not include any of those here, but there is not an error estimate for individual estimations.
Okay, but depends with the age and metallicity. Depends of the age or the distance, maybe.
Yeah.
Or you give a general error. I mean, my question was related. I mean, my question was if there is any dependence. I mean, also I am interested in the absolute error, but also if there is a dependence with the age of the cluster in the error that you
well, basically, we define 2 age ranges. So we say the young clusters that will be younger than 100 years, million years. We define an error in log age to be 0.15 or 0.20 deaths. And then for older than that, we define the error to be 0.1 or 0.15. So it's indeed an age dependence, but we only did that for these two very wide age bins. This is actually something I'm working on with a master student here, and let's see if we can get it to work.
I will see. I will read the paper anyway. Another question: would you pick up the supergiants in those clusters if they are there? I mean, or you just pick up the main sequence?
No.
The supergiants in the clusters if they are present.
Yeah, no, it's not only. I mean, here I showed just the example, which is only the main sequence, but we can only find. I mean, for this, that we said they are old. This is because we are able to find giants. I don't know if super giants, but yeah, if they are there.
I mean, my question is because it's very difficult. I mean, it's from the point of view of the stellar population modeling, it's very difficult to model massive stars, no? And the number of red and blue supergiants would help a lot to understand how is the mass loss. So if you have those stars for some clusters, well, that would help to model.
Yeah, well, basically, this is like the clustering process. It just if start a cluster together, so we picked it. Then we did this photometric validation. That's why we introduced the physics, right? And we used the models from Padova to train the network, plus the non-clusters. And we give a lot of weight to the main sequence and the red clump, let's say, for the estimation. So if they have a clear main sequence and red clump, so they are selected as clusters, otherwise they don't. But they can also have
okay, so they are there, and okay, good. So okay, excellent, thank you.
We also find examples of clusters with blue stragglers that
so you would raise the catalogs of the clusters with all the members and yeah. Cool. Great.
Actually, is it already in CDS for DR2, not yet for the EDR3.
Okay.
But I guess once the paper goes through the refresh process, if it goes through the refresh process, so I will get asked for the data. Yeah. Okay. But what I said about the blue stragglers, they are not introduced in the training set, but because we give much more weight to the main sequence and red clump, so you can have another populations there. I will not like turn the cluster down.
Okay. Thanks a lot.
Okay.
Perfect, thank you. So I cannot see another hand in the audience, but I have 5 questions. I will not make all the questions. I will ask you later. But the ones I want to make are both of them related with spiral arms and the nature of the spiral arms. You showed in the last slide. Well, first of all, in the figure 21, you showed this dependence of the spiral arms position only in the XY space. And my question is that there is a paper by De Battista where they say that the position of the spiral arms can have a dependence on the vertical direction. So you can have that the spiral arm has a position on the disc, on this plane, but while when you go up on the above the disc and below the disc plane, you can see that the spiral arms somehow can be a little bit displaced from the position in the plane. So this can, if you don't take cuts on Z, you can lose somehow the position of the spirals. If this is true, this is only for one kind of spirals. Do you have this? Do you have the same plot but making cuts in Z?
No, but how far from? I mean, which are the values of this?
I don't remember exactly the details, but if I remember, 1 kiloparsec above the display, you can have a meaningful.
Yeah, but here in this plot we are talking about 250 parsecs.
Because it's the very thin disk, of course. Yeah, 1 kiloparsec is going. But I don't remember exactly the details on how far from the plane have you to go to find this displacement. I will revise the bibliography and will tell you, because maybe it can be interesting to make small cuts on it to see the location of the spirals varies or not.
Well, honestly, I was not aware of this paper, and I didn't do this thing that you told me. But we are very contained on the central parts of the disk here. So.
Okay, this was the first question, and the second one, you said that you found that all the spiral arms are corrotating, but I can see in the plot you were showing, both the one where you are showing the pattern speed, this one. Well, there is Sagittarius. Just Sagittarius can be compatible with being with a rigid rotation. And when you go to this plotting where you show ages, the gradient ages gradient, you can also see that the Sagittarius shows somehow a gradient on ages. So you can see it in which one? In this one. In this one, Sagittarius, you can see somehow there is somehow a kind.
But okay, here you say that Sagittarius is compatible with solid rotation.
Yeah, with rigid rotation. And why that?
So individually, all of them are. So you are because you are comparing with this value here, but this value is also. I mean, I put down only the study, but they have a range of values here. So
okay,
there are other studies that take it to 20 kilometers per second per kiloparsec. So you would say Perseus. So
yeah. I understand. The point is that because both observations, well, not observations, so basically, well, yes, observations of external galaxies and also the simulations somehow tell us that the spiral arms in a galaxy, you can have a mixture of co-rotating spiral arms that are usually these ones that are generated by that are star-forming spiral arms that are in fact no related with a deep potential well. But you also have spiral arms that are kind of a rigid rotation that are related with the bars, and they can coexist. And I think that something that is accepted is that maybe in the galaxy, in the Milky Way, we would expect to have both, some that are rigid rotation, some that are co-rotating. So I think that we have no enough data yet to discard any hypothesis. No, that's why I think it's interesting to the things you can get with the early DR3.
Yeah, completely agree. I mean, you are the expert on this, so I completely agree. That's why I said also here this favors and not discard.
That's but well, in any case, it's extremely interesting to be able with the Gaia data to start studying the nature of spiral arms. This is something that we waited a lot of time to start doing that with observations. So it's amazing. It's a very nice result. So this was more a comment than a question. Sorry. And the very last one, because it's late. Can you use, at the very beginning of the talk, you said that you are rejecting a lot of stars because they are, they have high proper motions, because they are far away. Can you try to use all this rejected data, apply a similar method, and try to find groups in the rejected data? Has this sense? Have you tried it?
Well, I have not tried. If it makes sense, yes. If it's straightforward, no, because we rejected this because of the method of, I mean, the dimensions we're using and our methodology, basically. So, for instance, in the parallax, that would be the clearest example. If we use parallax higher than 7, that will be the distance of the Pleiades. Right? So, if we use parallax or try to find clusters closer than that, then you cannot define the same methodology, because probably these regions will be too small, and then the comparisons between the difference. So this distance here will have to be redefined, because yes, because of the projection effects, basically. So if that makes sense, I would say yes. If it's something just we can apply straightforward with our methodology, I would say no.
Okay, it was more for the high proper motions, no? Because maybe you can find something interesting coming from outside of the galaxy, because it has high proper motions. Maybe it's no, it's can be something. Maybe you can discover some stream, some hidden stream, or something like that. It was just an idea. And well, I have other questions, but I will not make them because it's late. So I will leave the opportunity to the audience to ask some other question if they have. If not, we can finish the seminar today. Okay, nobody else. So thank you a lot, Alfred, for accepting the invitation, for giving the talk, for presenting these interesting results. And we will invite you again after you get this new, you update the results with the new data, with the DR3 or the DR3 maybe. So I hope we can have you here again in the future.
Okay, it will be a pleasure, and thank you very much for inviting.
Thank you, and for everybody, we'll have another astro-seminar next week. Next week we'll have Luca Costatin that will talk about the observation of bars in external galaxies and the modeling of bars in galaxies. So I invite you to come again next Friday to the new IPARCOS astro-seminar. Thank you, everybody, and see you next week.
Bye.
Bye.
Bye.